Hello, everyone, and welcome to Embedded WASI World webinar hosted by LFH. I'm Sunny Tsai from the Linux Foundation, and we're very excited to have you join us today for a deep dive into how WebAssembly is shaping the future of embedded and industrial software development. So over the next couple of hours, you will be hearing from experts from Atym, Emerson, HMS Networks, Schneider Electric, Sony Group, Siemens, and Wind River. They will be sharing how WebAssembly-based containerization is helping create more portable, secure, and high-performance solutions from the cloud all the way to the edge. So just a few quick notes before we get started. This session is live and being recorded, and the recording will be available on the LFH YouTube channel after the event. We'd love to hear from you, so feel free to say hi in the comments and drop your questions anytime during the session. We'll keep an eye on the chat, and we'll try to get to as many questions as we can during the discussion. So now to kick things off, I'd like to introduce today's moderator, Jason Shepard, CEO of Atym and longtime leader in the LFH community. So Jason, off to you.
Thanks, Sunny. Thanks everybody that's joined. So yeah, today's all about WebAssembly and how it's finding its way into the embedded world. And so all the companies participating have been working with it and collaborating on leveraging the technology. It's an amazing technology with a funky name. As Stephen and our team says, it's not really assembly or web. But it's ubiquitous in modern web browsers, but finding its way into cloud native applications. And then, of course, we're talking today about specific to embedded and resource constrained devices. So throughout the event, we'll have a series of topics and bring people on and off throughout. We're going to start with a kind of a high level, more of a deep dive into WebAssembly and WASI, the WebAssembly system interface. That's Dan from Wind River. We will then talk about the efforts within the Bytecode Alliance to tailor WebAssembly or kind of really look at the needs for embedded use cases. Make sure those are represented, as well as some of the long-term support efforts that that group are collaborating on. We'll then introduce the Ochre container runtime, which is part of LFEdge. It's one of the projects in the umbrella that is leveraging WebAssembly to make it easier to deploy Wasm-based containers on resource-constrained devices. So we'll kind of dive into the technology a bit. Then we'll have a case study that is, we're applying Ochre to a real-world scenario, leveraging OPCOA as a connectivity protocol. So kind of modularizing a connector that you can then use across different platforms without having to kind of recode everything. So just kind of talking to the power of that portability of different functions that you can reuse. And then finally, we'll have a panel on various use cases and kind of the business impetus. Why now? Embedded has in large part been done the same way for a long time in terms of firmware development, how we do embedded Linux. We've seen containers coming into a lot of environments, but it's also been limited because of the footprint and various considerations. So why is now kind of right for relooking at how we do embedded? A few of the macro trends. I mean, devices, let's face it, are getting more and more capable, but we're also seeing increasing cybersecurity challenges. Just being able to collaborate across an ecosystem of partners. Edge AI, on-device AI is another big reason. But so we'll talk through that as well in detail. So with that, I'll hand it off to Dan with Wind River to dive into WebAssembly as a technology. Dan, you want to do the intro and then I'll drop out?
Hi everyone, thank you for joining this session. My name is Dan Milea and I work in the Wind River office of the CTO on emerging technologies. Today I'll be talking about WebAssembly and how it moved from the browser into the world of embedded systems and cloud computing. Next slide, please. Over the next 15 minutes, I'll walk you through a brief history of WebAssembly and how it evolved into a standalone runtime, how it compares to traditional containers and virtual machines, its architecture and the benefits it provides, and the role of WASI, the WebAssembly system interface, in the way we build and run WebAssembly applications. Next slide. WebAssembly was introduced around 2015 by the major browser vendors, Mozilla, Google, Microsoft, and Apple, as a portable low-level binary instruction format designed to run at near-native speed inside web browsers. Its precursors were Mozilla's assembly.js and Google's native client, and the initial implementation was based on the feature set of assembly.js. The goal was simple: enable developers to write code in languages like C, C++, or Rust, compile to a safe compact binary format, and run anywhere the browser runs. In 2017, we had browsers which supported WebAssembly. Since 2019, WebAssembly has been managed and standardized by the World Wide Web Consortium. By itself, WebAssembly can't directly modify the document object model, so in browsers, it is paired with JavaScript. But the real game changer is in its standalone use, WebAssembly outside the browser. Because of its tiny footprint, near-instant startup time, and strong security sandbox, it's perfect for serverless and cloud environments where low latency and quick spin-up are crucial, edge computing, IoT, and embedded systems where resources are scarce, or for running secure plugins or extensibility layers in applications where you need to safely execute code from external sources. Next slide. Let's put WebAssembly into perspective by comparing it with traditional technologies like containers and virtual machines. VMs offer the strongest isolation by virtualizing the entire hardware, but they are huge and slow to boot. Containers are faster and smaller because they share the host operating system kernel. However, the shared kernel introduces a security risk and makes their portability somewhat dependent on the host OS and architecture. WebAssembly occupies a sweet spot. Its modules are tiny, often in the kilobytes range, and they start in milliseconds. More importantly, WebAssembly provides a secure and isolated runtime for applications, a sandbox, which is above the OS kernel, meaning it cannot make direct system calls. The WebAssembly architecture ensures true binary level portability across different operating systems and hardware architectures. So you practically compile your code to WebAssembly once and then run it everywhere you have a Wasm runtime. Next slide. Security is one of WebAssembly's strongest advantages. Each WebAssembly module runs inside the sandbox, meaning it has no implicit access to the file system, network, or system calls. It can only access what the host explicitly allows. Each Wasm function is deterministic and side effect free, except for controlled host calls, ensuring predictable performance, an important feature for real-time and embedded applications. Because of its deterministic runtime behavior, WebAssembly is ideal for safely executing untrusted code such as plugins and third-party extensions in embedded environments. All memory read-write operations are subject to mandatory runtime bounds checking. This design mitigates common memory corruption vulnerabilities. Next slide. WebAssembly is built upon a stack-based virtual machine architecture, meaning it relies on a central operand stack for all computation. Instructions pop arguments of the stack and push results back. This design makes the bytecode simple, compact, and easy to verify, and it simplifies the runtime's job of translating WebAssembly instructions into native code. The compilation target is the VM, not the host OS, ensuring high platform independence and portability. WebAssembly employs a linear memory model, where memory is represented as a contiguous array of bytes that can grow dynamically as needed. Basic function calls use the stacks to transfer function parameters. The host can access WebAssembly pointer memory through a form of address translation. This translation is necessary for secure I/O operations and passing complex data structures between the host and the module. Of course, the reverse is not possible, since WebAssembly applications can't access the memory pointed to by the native pointer due to the sandbox environment. Next slide. Developing WebAssembly applications is straightforward. You use your programming language of choice to create applications, compile to a Wasm target, and run using an interpreter. Languages like C, C++, Python, Go, Rust, or many others are valid choices. Things get interesting when your application needs to interact with the external world. This is where the WebAssembly system interface WASI comes into play. WASI was officially announced by Mozilla in March 2019. The goal was to create a system interface for WebAssembly to run outside the web browsers by providing standardized access to system resources like the file system and networking. Instead of using OS-specific syscalls, WebAssembly applications call WASI functions like fdread, socksend, or clocktimeget. This allows a Wasm binary to run identically on Linux, an embedded real-time OS, or Windows, as long as a WASI-compatible runtime is available. Next slide. WASI Preview 1 established the basic I/O primitives. The current implementation status within WASI libc shows file system access is stable. Threads and sockets are being the current focus of the standardization working groups. The transition to Preview 2 is marked by the introduction of the component model with richer data types, synchronous I/O, and better language bindings. Features like garbage collection, 64-bit address space, and multiple memories are under development. If your application uses a WASI P1 target, there are some things you as a developer will need to keep in mind. When I started building more complex WebAssembly applications, I stumbled upon some missing features like C++ exception support in WASI libc, dynamic library support, or set jump, long jump. Pretty much go to on steroids, used mostly for error handling. But things are improving very fast. This is an excellent moment to mention the Bytecode Alliance Special Interest Group for Embedded and Industrial Applications. Its primary purpose is to address the challenges and advance the use of WebAssembly in embedded and resource-constrained environments, including industrial and IoT devices. Long-term support of WASI APIs is one of the many critical activities being handled within the SIG. Next slide. WASI security model is based on capabilities. Explicit permissions granted to WebAssembly modules to access specific system resources, like read from a directory or open a socket. Capabilities are fine-grained and prevent modules from accessing resources unless explicitly allowed. This model is essential for embedded systems where sandboxing untrusted code is critical. WASI provides low-level C++ bindings with higher language support like Rust in Wasm Time or Wasmark. These APIs enable developers to write Wasm modules that interact with system resources using familiar interfaces. For example, opening a file via WASI involves requesting a capability and using it to access the file system. The Wasm runtime mediates the WASI calls and translates them into host OS requirements. This mediation ensures security policies are enforced and provides consistent behavior across platforms. Next slide. Why is WASI such a big deal? Because it offers the same portability that Java promised, but without the heavy VM. It's fast, small, and predictable. WASI matters for embedded developers because it solves critical long-standing challenges related to security, portability, and modularity in resource-constrained environments. WASI defines a portable set of APIs for interacting with the host system in a safe and standardized way. The runtime, not your code, implements platform-specific behavior, and developers are free to use their programming language of choice, be it C or Rust or anything else with WASI bindings. A Wasm module built with WASI starts in milliseconds and can use kilobytes of memory. WASI truly enables the compile once and run anywhere paradigm. Next slide. WebAssembly development environments have evolved a lot, and now Wasm WASI is just another cross-compilation target. The WASI SDK includes a prepackaged LLVM-based toolchain, WASI libc, headers for WASI, and debugging and profiling tools. The mscript and SDK is also popular, since it can create standalone Wasm binaries which are usable in non-JavaScript environments. Tools familiar to developers like ObjectDump have their equivalents for WebAssembly, and I get a lot of good WebAssembly tools from the WebAssembly binary toolkit. Next slide. There are several popular Wasm runtimes today. Whammer, the WebAssembly micro runtime, is lightweight and optimized for embedded use. It currently supports WASI Preview 1 with Preview 2 support underway. Whammer is written in C. Wasm time is developed in Rust. It is the reference runtime maintained by the Bytecode Alliance and already supports many Preview 2 features. Wasm Edge is a cloud-native computing foundation sandbox project which supports all standard WebAssembly features and many proposed extensions, like garbage collection, SIMD, or exception handling. Wasmer is a pluggable multi-backend runtime written in Rust. It can use Whammer, for example, as a backend. Another popular interpreter is Was0, which is written in Go and has 0 dependencies. This means it can be embedded in applications that do not use an operating system. In the end, having many runtime choices allows developers to balance startup time, footprint, and performance depending on their application requirements and deployment scenarios. Next slide. For those of us interested in achieving the best performance available for our applications, WebAssembly includes several performance-enhancing features like ahead-of-time compilation, threading support, APIs for efficient ML inference, or SIMD. Ahead-of-time compilation is a method where the WebAssembly bytecode is translated into native machine code specific to the user's processor before the code is executed, in contrast with traditional just-in-time compilation, where translation and optimization occur while the program is running. WASI provides standardized neural network inference APIs for Wasm. It allows runtimes to delegate compute tasks to the best available hardware, CPUs, GPUs, or NPUs without changing the application. SIMD extensions bring vectorization to WebAssembly, improving performance for signal processing and machine learning workloads. WasmGC introduces support for non-linear memory allocations, meaning that porting a programming language to Wasm no longer needs to include the language's garbage collector. Next slide. WebAssembly brings together security, portability, and efficiency in a single runtime format. It's lighter and faster than containers, yet safer than native code. And with WASI, it provides a standardized system interface across platforms. And LF-Edge's Project Ochre provides the robust, lightweight infrastructure needed to deploy, manage, and secure WebAssembly applications on billions of tiny devices. And you'll get to hear a lot more about Ochre in the following sessions. Thank you.
Awesome. Thanks, Dan. Yes. So yeah, you've been working with WebAssembly for a while there at Wind River, right?
I have.
Diving in. A lot of acronyms.
Yes. There are just a few of them which, once you get to be familiar with them, you start using because it's simpler than to use WebAssembly everywhere and spell it as WebAssembly. Wasm works. And solutions based on WebAssembly also work, as I have plenty of empirical evidence with projects which you may not think of being WebAssembly targets, but they are. That shows that the ecosystem is good and allows building complex solutions using targeting WebAssembly.
Yeah. And then one of the, I think the key points that you made is, like there's the Java, from 30 years ago, the Java promise of write once, run anywhere. And what's different with WebAssembly is that it's a compile target versus a programming language.
Yes.
So it helps you package things very efficiently, but it's not tied to one specific language. You mentioned, C, Rust, Go, and there's other support coming online. So very key difference. Super lightweight, secure, and also any language.
Yep.
Very cool. Okay, well, we're going to switch to a panel. And in this one, we'll talk about the Bytecode Alliance's eSIGs, the Embedded Special Interest Group within the Bytecode Alliance. And so this is all about how do we create more kind of standardization specific to embedded/industrial use cases. So with that, Sunny, if you can bring on the panelists. All right. So, hey guys, thanks for joining. Let's go through kind of quick intros. Tell us a bit about yourself, your background, and then we'll kind of dive in. Merrill, you want to start?
Sure. Merrill, Harriman, Schneider Electric, system architect. I've been with Schneider for a good number of years and started messing with Wasm probably 18 months ago or so. We've been doing some very interesting activities inside Schneider and working closely with Jason and his team and Atym, and very closely with Stephen to help us develop some of this stuff. It's been an interesting ride.
Yeah, cool. Chris?
Yeah, so Chris Woods from Siemens. So been here for about 7-8 years now, and our roots to WebAssembly kicked off maybe 6 years ago when we started on the journey that I think Dan did a really good job of introducing earlier, where we're like, hey, we need something that we can run at the edge that's a little bit smaller than a container. What could it be? And that kicked off our investigation into WebAssembly. And from that, then exploring the ecosystem and getting involved in the Bytecode Alliance and the embedded SIG through that. So, and my role now is helping the business teams at Siemens adopt WebAssembly and trying to support the community as well.
Yeah, that's great. So Chris, you've been presenting on it for a few years, like kind of well ahead of the curve in terms of the potential and the possibilities.
Yeah, it's it started off with just the inkling of, I think this might be possible, to let's see what we can do, and getting the first prototypes up and running and being able to show that to the community. Like many big organizations, if you're going to adopt a new technology, it's really important to know that the ecosystem exists to support it. And that's one of the reasons why we got involved. And it's been a heck of a learning experience, events like these. And even as a participant, it's always good to hear and learn what others are doing. And you always take away a great bit of knowledge from it too.
Yeah. And you mentioned the importance of embedded. I always said, like, there's a lot of context missing when people talk about edge. Hey, it's tiny. The footprint's tiny, and to a data center person, it might be low gigabytes.
Yep.
An embedded, like a sensor, we're talking kilobytes, and so we'll get into that more as we go in terms of kind of ochre. So real time is a very misused word in terms of what that means, depending on what you're doing. So yeah, we'll dive into more of that as we go. So Stephen, quick intro.
Perfect. So I'm Stephen Berard, CTO and co-founder here. Jason's partner in crime at Atym. I have a deep background in software, been doing a lot of OS work, spent 10 years at Microsoft in the Windows kernel team, always on that edge between the underlying operating system and the hardware that powers that below that. Done a lot of work in the IoT space, networking as well. Been involved in WebAssembly and what is now Atym for, I think it's about 3.5 years now, to use what Chris said, might be possible, looks kind of interesting. That's kind of how I got into this. And then as we dug deeper and deeper, might be possible turned into, that's actually possible. And actually it works really well. And so it's been a great learning experience and a really good ride. And I'm excited about where we've gotten to at this point and where we're going. So should be a good discussion today.
Yep. Very good. Cool. Well, let's kick it off. Chris, and you've been involved since the beginning, really helping to shape this. So kind of start with you is, how did the eSIG come together, and kind of what's the mission?
This is a good question. So we did exactly the same things everybody here. Hey, is this possible? Does it work? Oh, it does work. And then through that, we got involved in the community and joined the Bytecode Alliance. And through the Bytecode Alliance, we started to discover all the other teams from different companies all working with WebAssembly. And WebAssembly has so many different applications. And we talk about, and Jason, you mentioned it, the different sizes of devices and what we really mean by the edge. And so there was companies trying to develop cloud edge solutions, working on essentially mini data centers. And then there's folks working on effectively set-top boxes or Amazon Fire Sticks or that sort of stuff. And we bumped into the Amazon team and they were doing Amazon Video Prime, and they were rolling out WebAssembly. So if you're watching Jack Reacher, you're probably watching it via WebAssembly. Then we heard that the Disney Plus streaming service was using it as well. So we started to discover all these different services, and we got involved in the WAMA open source runtime. And through that, talking to Intel, and then discovering the folks who are on the other side of the planet from us, folks in Asia who are working on it, and Xiaomi and Huawei, and the fascinating things going on in China. And we discovered after working with these guys for a while that, just as the cloud people had a direction and the web people have a direction and the set of needs, that there was a common set of needs appearing for the WebAssembly embedded space. Mainly we're dealing with C. We're not really dealing with interpreted languages, so we had a different requirement set. But starting to work on maximizing throughput. And you mentioned real time, and it's a running joke inside Siemens that every team in Siemens has a slightly different definition of what real time actually means. So whenever you say real time, there's usually an argument. So
I was having a discussion once at a conference like a long time ago, and I was talking with someone that does industrial networks or industrial use cases and someone that does building automation, and everyone's talking about real time. And I'm like, all right, guys, we're talking past each other. What do you mean by real time? A microsecond. And deterministic. What do you mean by real time? 15 minutes.
Yes. It's that's it exactly. And like many big companies, Siemens has building technologies, and we have factory automation and railway systems. So there's a huge family of products where there is applicability for WebAssembly, but everyone has a different definition of real time. And we're trying to do the profiling and the analysis, and that was our first major contribution. Was here's the timing, here's what we found, here's how the different runtimes start to behave, here's where we think it's useful, here's to watch out for with your latency, here's where there's some jitter. This is how we were configuring it. And really that was to share with the community what we'd found, but also get the feedback on what other people have seen too. And through that, we got a collection of people together who all said, look, we've got a slightly different need. We're embedding these things in ROM images and small devices. Our tool chain requirements are a little bit different, and they matched what we're trying to do. So with that, we set up the Embedded Special Interest Group to try and work on these problems, try and tackle what we saw as common requirements, and essentially to pool our resources. We're all heading in the same direction. Why not work together on it? And Siemens makes money out of the building control solutions and have our factory automation solutions. We don't make a WAMA runtime. That's not the industry we're in, but it's part of what we want to use to develop our products. And if we want to do that, the ecosystem should be successful and we should contribute. So hence the e-sig and how we got involved in it.
And then so you and Stephen met back, and I think at Atym, as we were sort of starting to build with WebAssembly, build our commercial solution, we started catching your presentations. We're like, we got to talk with that guy. And Stephen, so maybe kind of talk a bit about how you got involved in the e-sig and working with the group.
Sure. So, I started, as I mentioned before, like three and a half years ago, investigating how we can use WebAssembly for powering our containerization technology and what we can do on the embedded space. Looked at a number of different virtual machines. There wasn't many of them that can honestly run in this footprint. And ultimately did some prototyping and settled on the WebAssembly micro runtime, or WAMR, as it's generally called. Bytecode Alliance project, had a bunch of questions, trying to understand where the feature roadmap was and whatnot. So I got involved with the Bytecode Alliance and the WASI special interest group that's part of the W3C WebAssembly group. And obviously came across Chris and a lot of other folks, and so I was like, hey, I got this problem. Like, oh, you got that same problem too. And so like, hey, let's talk. And we started saying, hey, what are the needs here? And if you look at what's going on with WASI, there's a lot of really exciting things going on about on WASI, right? And the uses are incredible. When you look at the embedded space, there's some incredible use cases there as well. And a number of the things that we were looking to do really lined up well with Chris and a few folks at Amazon and Sony and a few others. And so When we started talking about like what can we do in the space, it made sense to create that special interest group. And then I think Chris is the one who raised his hand and said, "Hey, I'll kick this off and get this started." And then a number of us piled on. And it's a really interesting special interest group because there's a fairly large group of people that are interested in this space and doing things on embedded, which to me is actually quite a surprise, right? You think WebAssembly, you think cool apps on the web, you might think Lambda functions. Those are all great, distributed applications, cloud native. But the number of people doing really interesting things, and Dan mentioned it earlier in his talk, on these embedded devices in these small footprints, was quite surprising. It's normal for me now, but it was quite surprising at first just how many people were doing this and the kind of things that we're doing. And so it's been just super exciting. We've got a lot of things that we're trying to move forward, which we'll obviously talk about with the rest of this discussion today.
Yeah, cool.
Yeah, one of the things that one of the things that got me when we were setting up the embedded special interest group was having Xiaomi come and say, we've got 1.5 million devices deployed worldwide running WAMA, and you're like, wow, that's pretty amazing. So
yeah, I mean, the technology is everywhere. Like we said, it's ubiquitous in browsers, but a lot of people don't know it. Like many great technologies are running in the background, and it's really about how you use it and all that, but kind of finding its way. So Merrill, you mentioned you've been working with it at Schneider for about 18 months. Like, kind of maybe like talk through how did you kind of come into the picture with the eSig and a little bit of kind of what you guys are looking to get out of it and kind of help the community.
So I've been doing the software-defined automation stuff for, I don't know, over a decade anyway. And most of that's been around Docker container kind of functionality, trying to bring workloads to the edge. And in that vein, a parallel LF Edge project, Margot, that both Siemens and Atym happen to be members of. Through that, I met Stephen and we started talking a bit, and it became obvious that this is not just a Docker container type or containerized for edge devices, but could really be used for small devices. And
microcontroller based.
Microcontroller based devices, yes. And so digging into that a bit more, we realized that there is a real benefit here. There's a lot of capability that we could be leveraging deep into our industrial networks. And so I started running around raising the Wasm flag at Schneider, and we now got a group together, and we're doing some really interesting developments, and you'll hear about a little bit of that later. So
yeah, I think we met initially on one of the Margot meetings, and we're like,
yes, yes,
we got to talk. And I think it's key. It's this isn't about replacing, certainly not Kubernetes or replacing Docker entirely. They all have their place, but when you look at the continuum from obviously the cloud and then a regional data center down through kind of on-prem, metro data centers, on-prem, the factory floor, then you start getting into kind of the embedded world, like that boundary between the physical world and the networks and applications further upstream. And we're talking sensors, controllers, robots, drones, vehicles. Could be many things. Your toaster, that's a connected toaster. But it's very challenging when you get into the embedded space, because a toaster is a little bit different than a car, and it's a little bit different than an industrial controller, and there are different needs for all of these things, and so there's a lot more considerations. And then of course there's just the resource constraints when you get down to like kilobytes of memory versus gigabytes. So the whole point here is, how do we augment, as you guys are saying, how do we augment WebAssembly for the needs of this class of device, embedded device, both CPU and MCU based. So with that, I'll let's shift gears. So kind of specific to embedded. Maybe Stephen, I'll kind of start with you, and then we'll go around. But like, what are some of the specific things that we've got to kind of have to close the gaps on for these use cases?
So that's a great question. There's a number of things when you look at building software that you need to have in place, right? You need, obviously you need the support for the language and the tools to compile that and to build and link that. You need the runtimes or the operating environments to govern that. So you need those implementations. Obviously you need validation testing and lifecycle management. And so there's a whole ecosystem there. And so when you look at things like WebAssembly is a spec and some implementations, right? And so those are very good to have. They're a great starting point. They're absolutely necessary, but we need stable compilers, right? We need linkers and debuggers, and we need that. And for the most part, we have that, right? We have WebAssembly support has been in the LLVM toolchain for, I'm going to get it wrong, but at least 5 years, and it's been upstreamed for quite a long time. So that's a very robust implementation that's been around for a long time. It follows the standard, so it evolves as the standard evolves. That's all there. But when you're building software in the embedded context, you need a stable compiler. You can't be taking the latest version of the compiler every week, right? That doesn't work well from a testability, from a reliability, from a long-term support area. So one of the big focuses that we've been doing in the eSig is to build a program around long-term support for that. That's not to mean that we won't follow the standards or add new features or do that, but we need that stability, and then we need a path for how you adopt those new features or new technologies or new releases in a meaningful manner, right? We see this with things like Linux. Linux has had a long-term support methodology for quite a while. The Zephyr operating system, which I'll talk about later, has that as well, right? So we're just following a lot of those same things, but bringing that into the space. So I'd say that's one key thing from a sort of ecosystem perspective, and that's something that Chris is and all of us on the eSig are really working towards. On a more technical side, there's a few things that you tend to need on the embedded side that are not quite part of what you would see in traditional WebAssembly, right? You generally will need low-level access for devices. A lot of these devices, for better or worse, are memory mapped I/O, direct, DMA access, right? So, for example, if you're doing object detection on a small device, you need to be able to very quickly DMA in a frame from the camera, do something with it. If you have to copy that memory back and forth and do that, you're not going to be able to get high frame rates. You're not going to be able to meet your performance, your battery life, your energy thing. So there's a few of those things, and those are somewhat at odds with the pure sandbox model that is in the browser, right? It's just a different environment, right? Neither one is correct. They're just different applications. So there's a few of those that we're working on, and we have solutions in the works to deliver those. So there's plenty more, but I think those are the two I would start with on the top of my list.
Merrill, what are some of the things that are top of mind for you guys? You mentioned a bit of them, but kind of anything you would add in terms of interest areas for Schneider?
Yeah. So when you think about Wasm applied to an industrial control system or industrial application, you mentioned toasters, you mentioned automobiles, but industrial's a little bit different than that, because when you put a sensor out in the field, you got to expect that it's going to stay there for 10, 15 years. And so in order to have Wasm based solution down there at that level, where you've got something that's going to be in place for a long time, you need to be able to make sure that you can maintain that device for many, many years. So that LTS solution becomes paramount. Without that, you'll never do Wasm down at that level. So and you also need support for some of the things that Stephen was mentioning. If this solution has got any notion of real time in it, then you're going to have some significant improvements over some of the stuff that is being done, like, for example, in the component model for when you apply that to embedded. Some of the things like semaphore protection or semaphores and networking and I/O support and things of this nature need to be there in order to be able to make this a viable solution for deep embedded devices. And yet, the fast boot time of a Wasm module is really helpful. We envision that you can extend the functionality that we have in Docker-based applications down deep into the network with deployable workloads onto very small devices because of these small footprints, fast startup times, and the ability to run really complex solutions down there in very small modules, AI even down at the very edge. But you have to have something that you can maintain for many, many years. So the LTS is going to be the driving factor that brings us forward.
Yeah. I call it Docker on a diet.
That's right. Yes.
Yeah, and that's the key point. So the long, like just the install time for these types of systems, and then the closer you get to the physical world, the more heterogeneous the I/O gets. You're up in the data center. We're talking Ethernet connections. Could be on fiber, of course, but it's Ethernet. It's IP traffic. You get down into the physical world, and the factory floor, and out all these different locations. It's Ethernet IP or wireless HART, or all these. We're going to talk about OPCUA here in a bit, which has been an effort to kind of unify some of these protocols, but Profinet. So it's there's a lot of variation that you have to accommodate. So, Chris, your thoughts on? I mean, obviously you've been looking at this a while, as we've said, but your thoughts on some of the stuff that you think is important to focus on.
Yeah, I think Stephen and Merrill captured quite a bit of it. WebAssembly, we benefit from the work that's been done in the web, but we are also exposed to the web development model. And that's very much a rolling update. You just push out a new browser update. I mean, we've all seen it, open Chrome, there's a new update, you have to install it. And the benefit of the web is they get all the usage figures. They know who's developing what apps, using what features of WebAssembly, and they can push updates at the appropriate time. And it produces this rolling development model, which is fantastic if you're in a web browser, but kind of sucks a little bit if you're trying to lock things down and support it for 10, 20 years. And that's where the LTS comes in. It's like, hey, we really need to have this. We need to have our tool chains in sync with our runtimes. So we've got the same feature sets on both sides and everything works. We need some extra help in the debugging space, make that experience better for customers, building applications for their embedded systems. What can we do there? And then, I think there is a benefit, of course, to WebAssembly in terms of obsolescence, because you have that abstraction from your hardware. So should you need to change your hardware in the future, it's possible because your compiler and tool chains are kind of isolated from it. But then you need to have the stability in that. You need to have the memory throughput and capacity. I think Merrill picked up on that one too. So when we set up the eSig, we initially looked at the component model, and its goals are great. It sounds like a fantastic goal, true interoperability between languages. But the mechanism and the overhead of implementing the current version of it, it's just too CPU intensive, too costly to use in an embedded system.
Not tiny.
Not tiny. It could be tiny, but not tiny. I mean, the smallest we've ever gotten it down to, and we did this with with Stanford University, we got it down. We got WebAssembly down to 500 bytes, and that was 200 bytes for the runtime and 300 bytes for the memory required for a function. It's like a really simple function in WebAssembly. So we can make it really, really small, but you can't use the component model in that sort of context. It just doesn't fit. So yeah, the throughput, the how do you map onto your different I/O systems on an embedded device? What do they look like? So there are problems and common APIs that we need to develop for that. And there's some fantastic work coming out of other folks in the embedded SIG, like University of Ghent, working on systems and APIs for this, which is really great to see. There's other use cases that are coming in, things you wouldn't even think about. We've had folks from Collins Aerospace join the embedded SIG to talk to us about how they could use it in aircraft interiors. So you're like, wow, there's a huge remit of angles here. But it all comes down to enabling that high throughput, providing that secure and reliable mapping to the device's capabilities and its feature set, and getting a stable, solid runtime development debugging environment where the runtime and the compiler are kept in lockstep and have that long-term support. They're all the key enablers. That's what we've been trying to work on in the eSig, but it's been a fun journey.
Yeah, cool. So there's been some questions and comments, online. That we'll kind of work in. I'll put this out to the group. One of the comments is very concerned about IP protection when it comes to the edge, or embedded systems. I call it source code soup when you're working in firmware. You're kind of bringing all this stuff together and compiling it together. And we'll talk a bit more about this in the use case panel at the end, but your guys' thoughts on kind of IP protection and how all this works. And then of course, there's always the question of, the boundaries between standards and open source and, proprietary solutions and protecting IP. Thoughts on how that kind of comes together and how that ties into the work at the ESIG?
Do you want
me to go first?
I can jump in real quick.
Sorry, for the group.
We're all jumping at the same time. No, what's really interesting is, you look at how you traditionally build embedded systems, everything gets linked together into a single target, right? So you have this sort of like a big bang integration where everything has to be there. And if you're licensing, software for a protocol library, for example, right, from a third party, you generally need to license that at the source code level, right? So if you're the company doing that, you have to license that out and trust that your IP is going to be protected. One advantage of WebAssembly is we can ship now an actual binary, right, with known imports and exports that can be called externally. So think of it like as a binary, like a DLL or something that I can load and call. And so that allows you to encapsulate some of that and preserve some of that IP. And then there's some really fancy research going on around, running that even in a secure enclave if the hardware permits it, and doing secure computing, confidential computing, and things of that nature that are really exciting. We're not doing that. We're not going that far yet, but those technologies do exist, and there's a lot of research going around that.
Yeah, I think a lot of people are worried about, hey, if I deploy my application logic as WebAssembly, somebody could grab it and reverse engineer it and find out what goes on inside it. You could, it's true. But like Stephen said, my career, I ended up doing mobile phone systems and working with a company that was working on Symbian, and you get the entire source code for that platform. And then they moved to Windows when Windows was on mobile phones. And they're like, hey, Microsoft doesn't give us the source code. We just get a binary blob, and we're told to build a device driver, right? Because they don't want us decompiling their code, right? And yeah, that's kind of where we're heading to. And there are parts where you would want folks not to decompile stuff or debug into it. I think mainly it's the debug story, because ultimately, if somebody really wants to reverse engineer the source code on something, there's tools from the NSA and Ghidra, and you can do lots of funky stuff with it. But for practical reality, it provides some limitation on scope, not just from an IP protection point of view, but also from a developer experience. I'm sure Siemens, like many others, we're developing products where we partner with an OEM who integrates their code with ours. And in that environment, allowing the customer to debug our code would cause the customer just as much confusion as it would IP protection issues. They're going to see stuff that really doesn't impact what they're doing. It just causes confusion, and our support teams would probably get flooded with phone calls like, what the heck's this doing? Like, well, you don't need to know. It doesn't really affect what you're working on. So there is some work there, and part of the solutions you can do. There are things you can keep it in WebAssembly, but the beauty of WebAssembly is that pluggability. So you can keep it as WebAssembly, or you can say, hey, this particular component, this logic, it's native, it's locked up. You don't get to see it. We don't go ship it as a WebAssembly binary. It's a native binary. So there's bits and pieces you can do to do that. But really, I think it's kind of a balancing act. And it's miles ahead of where we once were with a single binary blob. As Stephen said, it's come a long way. It's certainly a lot more compartmentalized than it has been before. And that has to be a good thing.
Yeah, we're in effect appifying, embedded. Merrill, your thoughts on the kind of IP side?
Well, I was just saying you have to have a real reason that you want to get in there, because it's not going to be trivial. I think if you're extremely motivated then it's not going to matter what you do.
And it's par for the course for many technologies, unfortunately.
Right.
Yeah, it is. But I think when you see what folks are doing with Ghidra, and it's just nuts. What reverse engineering the entire Zelda source code. I mean, okay.
There was another comment about just this notion of over-the-air updates and the bits across the wire required. Obviously with traditional firmware, if you want to update a device, you're compiling that new firmware image and then flashing the entire device. If you lose power during that process, you're quite likely going to break that device, and then you're driving a truck out, to the field. And usually when it's on these types of connections, it's remote, especially kind of lower end stuff like that. So kind of maybe some comments on this comment in terms of the benefits of these fractional updates.
Yeah, so because of the small size of a Wasm module or a Wasm container, if you're using that technology, doing something over the air over a very intermittent or very slow network, I mean, like you said, if you're pushing down the entire thing and you interrupt it, then you're screwed. But with this very small module with an incremental update, it lends itself well for that kind of a solution. With and we look at that as well as for very remote. Think of a pumping station on a pipeline out in the middle of Alaska, right? So that your connection out there may be weak and slow, and if you're downloading the entire thing, you're probably going to be you're at risk. But if I can just update just the module that needs to be updated on that device for a security patch or whatever reason, added capability, whatever I'm doing, then an OTA solution is much more resilient for this kind of thing.
Yeah, 100%. You go from traditionally flashing the entire ROM image to like, here's a subset of what I need, and it's only this little module that I'm loading. And you can break your application up into tiny modules as well, so you don't have to update the entire WebAssembly application. You can update a subset of it. So it becomes really very flexible and very lightweight. For that example of the 500 bytes, the ROM image for that was 3K, and it was 1.5K over the air. So it's really kind of tiny. It's something that's totally doable over a LoRa connection.
One thing I'd add on the update side too is, again, by breaking these into smaller modules, you can have a module that is certified, right? You can get a protocol library that's certified for something, right? And you can update that, and that can be updated at a different cycle, right? Potentially that's a licensed component from a third party. And as that evolves, as that life cycle happens, right, a new version comes out, you validate it, it gets certified, then you can deploy just that part. And so you add a lot more pluggability. And we've seen this on the web, right? This is the same story we've seen in cloud native, where I have components that I use and I compose into my application, and I can reuse those. And so by breaking them into modules, you can obviously reduce the bits on the wire, but also you can get sort of that predictability, right? You can get certification, and you can break that big bang integration, deploy it all at once thing. The other thing is, as Merrill said, the risk of bricking a device, right? If I have to flash the full firmware, I may not have enough room on that device to store the old and the new. And so a lot of these devices, they go into like a kind of, they might have a small recovery bootloader, but if you start overwriting the firmware and that crashes, recovery is either impossible or very slow or very difficult, right? But if I'm not full application, I'm just updating that little bit, I probably can have the old version of the component and potentially even keep it running while the new version is downloading into a spare flash. And when that comes in, I can validate it and it's like, good, swap them over and not even have downtime. So not only are you improving, the amount of bits that go on the wire, but you can actually keep uptime much higher, reduce errors. And, again, if you're downloading a binary in the background and you've got some network foible, you can restart it, right? But you're not in this offline state now because you had to put it into, firmware update mode. So there's some really good stuff here.
Speaking of smart toasters, that's one of these things. Embedded, the nature is changing when we look at AI, and we'll talk about this in the last panel and some of the business reasons. But a device that set it and forget it. It does one thing for its entire life. I'll only update it if absolutely necessary for a lot of the reasons that we're talking about. Otherwise, just keep it running. When you start looking at things like AI on device, it starts to change the update frequency, because that model is inevitably going to evolve over time, and your software defining that device. So yeah, we'll talk more about that as we go. I wanted to circle back to LTS just to kind of, and we've talked a little bit about this, just kind of get your thoughts. I mean, there's obvious ones, long-term support is, I think, sort of built into the name, but just, get your thoughts. This is a fairly new decision from the work group. I mean, obviously it's these companies. We mentioned Amazon, Bosch is involved, Sony, Midokura, Intel, a bunch of different folks. I will say, if anyone that's listening would love to get involved, reach out to any of the guys here, and we can kind of pull you in. But this is all about community effort. But yeah, just some thoughts, on the LTS effort and kind of the goals and where you see it headed.
Yeah, so I think we're all facing the same. We've all just talked through some of the amazing benefits of WebAssembly and the micro encapsulation that we get from it, which is really awesome. But in order to deploy it at scale for the products and lifetimes we need to do, we all face the same challenge and the same costs. The LTS should help address that for everybody and do it in a really cost-effective way, where we've all got a choice. We either do it in-house and on our own and bear the entire brunt of the cost, or we collaborate and share that burden. And that's really what the LTS is all about. It's like, let's do this. If it's successful, the impact goes far beyond embedded. It would impact the rest of the ecosystem as well. It's going to be the first fully stable tool chain and runtime environment where we keep everything in sync, provide that support, security support, make sure it's fit for rolling out. We're already conscious that whatever we do today has to be compliant with some of the European regulations and cybersecurity and resiliency that are coming through. So we've all got to address those problems, and we can do it together. So the benefit for anybody using WebAssembly is that reduced cost and the stability that comes with it. So yeah, Jason, thank you for asking for folks if they're interested in coming along to the eSig. I would welcome them with open arms. It'd be great to see them there.
I borrowed this phrase from someone long ago when I first started, in open source with the Linux Foundation like 10 years ago. It's we need to avoid undifferentiated heavy lifting. This is not the best use of time, and standards breed scale. Final thoughts from Merrill, you and Stephen on kind of LTS.
So the promise of LTS is what it made our view of Wasm go from science experiment, happy engineering kind of stuff to something that we could take seriously. Without LTS, this would just be maybe we could deploy some apps on it or something like that, but it was never going to be anything that would be mainstream in our products or something that we could really leverage. With LTS, there's a promise here, and there's a lot of potential for deployment of apps, services. I hesitate to use the term microservices. Maybe nano services is better, but services and capabilities that we can deploy onto the devices and rolling small updates and so forth. But we can't do that without having some standard ecosystem that we can leverage. And even going back to the concept of Margot at some point may bring in Wasm into its fold as well. So having a Wasm-based Schneider application running on a Siemens sensor is not out of the question at some point in the future. But we can't do that without LTS either.
Real quick, I mean, you guys both kind of hit the same points I would do. But one thing I would add is, when you look at things, I spent some time in the IoT space, you look at the entire ecosystem of like communications and silicon suppliers, software suppliers, protocol libraries, machine interfaces, cloud data services. Like that's a huge ecosystem. And one thing I learned in there is like any company trying to like own all of that and do it all themselves is just going to eventually go out of business. Like even large companies like Microsoft that seemingly have like all the money in the world, they're not doing that, and for very good reasons, right? And so there's a reason why Linux is so popular, why it's used so ubiquitously. There's a reason why Podman and Docker and open source technologies are used there, and then people build upon them, right? So rather than having to build that all myself, I'm sort of limited in what I can do from an organization in terms of time, resources, and opportunity. But by leveraging that, as Jason said, probably much more eloquently than I, open source and standards deliver scale. That allows me to build on top of those things. And so I can focus on building the things that matter to me and adding value back to that community. And then we can go compete with and go spend time on the things where we're actually competing and adding unique value, for Siemens or for Schneider or for any other organization out there. And so I think what really excites me about this is the group is getting together and saying, hey, these are the things we all need. Let's work on this together. Like, oh, you're good at compilers, great. You can work on stabilizing that. You understand how to deal with CVEs and build a security program. Like, okay, we're going to create a group around that, and these three companies will participate. Somebody else will work on performance. Somebody else will do research on debugging and things of that nature. None of us could do that alone, but together we can actually achieve quite a lot. So it's very exciting.
Cool. So thanks guys. Really appreciate the insights, and we've enjoyed the collaboration, and lots of work to do, but it's all for good reason. Actually, there was a question. So there are a couple questions that I think we'll take as we get into some of the other topics. There's one on how can Wasm-based containers help in kind of drone and robot development. That's a great one for us to address in the use case panel at the end. Stephen, there's one on kind of that I think would be good for the Ochre session. One of the questions was, how does WebAssembly and Zephyr play together? Which is like literally like a great segue into the Ochre topic, which Stephen, you'll dive into. So with that, we'll close the panel. Thanks again, guys, and again, looking forward to continuing to work together in the eSig.
Thank you.
All right, very good. So Stephen will stay on. I'll give myself the hook and leave for a bit. But yeah, let you dive into Ochre, which is the Wasm-based runtime within LF Edge.
Excellent. So welcome everyone. If you're just joining us, my name is Berard, co-founder and CTO here at Atym. I'm going to talk a little bit about Ochre. Ochre is our open source core, and it provides that containerization runtime. So to give you a little bit of background, what you're seeing here on the top is a bit of a snip from the LF Edge Edge taxonomy. So we talked earlier on about how Edge is very different for very different people. Real time is different for different people. Everybody has their own definition of this. So the LF Edge group got together and they came up with this taxonomy. If you've not seen that paper, it's a great read. And they start on one side and they go from these data centers, these centralized data centers or cloud data centers, and they go all the way down to these constrained device edges. And so what you see in this continuum is a lot of commonality. We scale down processors, we scale down memory, we scale down the software systems. And then we get to a point where that scaling down just isn't possible anymore. And we've drawn this here as that vertical line that we call the Linux barrier. So you can take technologies like Linux and Kubernetes and Docker and whatnot, and you can move them left, but you can only go left so far. At some point, you don't have enough resources to run that software, run those systems. And with WebAssembly, as Dan introed and as we just talked about, that opens up a tremendous amount of opportunity here. It allows us to provide true virtualization and deliver a lot of the same experiences you have on the right, but to devices and systems on the left. Particularly when paired with good well implemented, full-featured operating systems that run on these embedded devices, such as Zephyr. And so Zephyr is actually our reference RTOS. So we use the WebAssembly micro runtime and Zephyr as our reference RTOS. We can support other RTOSes as well. We can also run on Linux, but Zephyr really opens up a lot of possibilities for us. So next slide, please. So we'll talk a little bit about Ochre. So enter Ochre. Ochre is a managed container runtime project for constrained devices. The idea here is to deliver that same experience you get with an OCI container solution, such as Docker or Podman, but to do it on a class of devices where Docker and Podman just can't run. Our footprint is about 2,000 times smaller than traditional container runtimes. The goal here is to support apps written in a plethora of languages. And so WebAssembly is, again, one of those technologies that allows us to do that because it's a compile target. So anything that can compile onto WebAssembly, because it's just effectively a virtual CPU instruction set, can run on top of the Ochre runtime. A number of things that we build around that. We build a lifecycle management around that. So you have that same containerization, start, stop, pull, push paradigm that you have with traditional containers. It is designed around a zero trust security model on capable hardware that'll even be rooted in silicon. It's an LF Edge hosted project within the Linux Foundation, and it's got an Apache 2.0 license. Next slide, please. So let's talk a little bit about traditional firmware and how we turn that into containerization. So on the right, you have that traditional firmware, and we discussed this a little bit in the previous session, where everything gets compiled into a single binary image, a single firmware image. That means I have to have all the source code. That means I have to have a tool chain that can compile all that together. And while that sounds pretty mundane, it actually can be quite a challenge. If I'm given source code that expects a particular version of the compiler or particular flags, compiling that with my code that might have different compiler versions or flags or options could be quite tricky. It also requires me to have that source code so the IP is potentially exposed. And then obviously any change in any of that source code in any part of that supply chain requires you to rebuild everything, create a new image, and then deploy that image. So even the simplest case where I have a one-line security fix requires me to rebuild everything, relink everything, retest and validate everything, and then reflash everything, right? And so that there's actually obviously a lot of friction here. When you look at what's happening on the cloud native side, this is something that Jason and I looked at, and it's a world we've both spent a fair amount of time in. You don't do that. You build things as these modules, and you run them inside of these containers or virtual machines, and you can run and compose these together, and you can update and deliver those at a different time, at different cycles and different cadences. And so now those things become a deployment time decision, and deployment time specific, not compile time specific, and that's really important. And again, as I mentioned before, you can actually deliver these as binaries, right? So I don't actually have to give you the source code. I don't have to tell you how to build it. I can give you something that's worked. I can potentially give you something that's fully works and is also certified. And so that helps protect IP, that helps provide reliability and robustness. And again, in places that require certification, that helps towards that certification process. I think one of the big things that I would say here too is it supports asynchronous code and app development lifecycles. If you've ever worked in a large organization, like getting everyone to check their code in on time and link all that together and then build that into a single binary and deliver that works fine in small groups. But when you do that in very large organizations where you're getting a protocol library from one department and some machine logic from another and some AI from a third, that becomes a very difficult organizational problem. And when you can containerize those and deliver those in separate cadences, that becomes a much easier thing to deal with, especially as large organizations. The other thing too is, we mentioned this during the panel discussion, is because it's now broken up into modules, you can deliver these incrementally, right? So I can update, for example, my machine learning model, right? So I might train that over time, it might improve, and I can deliver that. But the rest of my application doesn't have to change. So I just have to deliver that one incremental update and deliver that there. And then finally, because we actually have containerization, these apps run in isolation boundaries, right? There's a sandbox that WebAssembly provides. And so code running in one container can't access or can't even address or doesn't even know about the existence of code running in another container. Contrast that to traditional firmware where everything is generally in a flat address space. Yes, on many of these microcontrollers, we have things like trust zone, we have things like memory protection units, but those are limited in functionality, and they're often limited in quantity if they're even available on there, right? So those environments are not general purpose computing environments. They're not like what you would have in a normal PC with process boundaries and memory management units and things of that nature. So we can provide a lot more defense and depth on these platforms. So it's not just taking this firmware and moving it over and running into these containers. It's providing additional values both from an organizational perspective as well as from an operational security and management perspective. Next slide, please. But this is not only limited to microcontrollers. I mean, we talked a lot about microcontrollers. We talked a lot about embedded and constrained devices. But we can also run this on larger machines, on larger devices that have traditional CPUs. We recently, earlier this year, released a port of our runtime for Ochre to Linux. And so now you have a runtime that runs on Zephyr, and we have a runtime that runs on Linux. And you can run the same code, the same binary across both of those environments and get the same experience. And so that provides us the ability to do a number of really interesting things. It allows me to say, hey, I might want to start and do some of my prototyping on Linux because it might be faster for me to develop. And then when I go to deliver that, I might deliver that onto a Zephyr-based host. Or I might have a multitude of different devices, some microcontroller-based, some Linux-based devices, and I have code that I want to run across all of those. And traditionally, I'd have to target those and have different versions of those and manage those dependencies. Now I can build that once and run it across both of those environments. And we think that opens up a huge amount of potential opportunities. And then also what I really am excited about is because I can run this on Linux, I can run this on my desktop, I can start development, and I don't actually have to wait for the hardware to be done, right? So I can actually start here, and when I'm ready, I can actually move that over to the embedded system. So that's, I think, some of the incredible opportunities we have here. Next slide. Real quick, talk a little bit about the architecture here. We have strived for a common architecture across both platforms. And so today we have a common code base for Ochre that spans both of those. So the WebAssembly runtime, the Ochre runtime that wraps around that, that's the same code on both platforms. Yes, there's some specifics that are related to the platform, but those are generally limited only to the things that touch the operating system. Obviously, system calls are a little bit different on Linux than they are on Zephyr, right? So there's a little bit of variability there. But we're actually working as well within both the Linux and the Zephyr community to see what we can do to unify that, to have our code be even more common. But today, I would say it's somewhere well above 90% of the common code across both of those. So next slide. I want to talk a little bit about performance, and because that's generally the question I get at this point when I start talking about this. Like, it's all great, but what's the cost? What do I have to pay to get that? And so let's talk about performance in a couple of different dimensions. First, how small can we make a container, right? We talked about WebAssembly. Well, WebAssembly creates very, very compact binaries, right? You can build a really, really tiny binary. And then when we wrap that in a container and deliver it to the device, we maintain that small footprint. And so we've built containers that actually run that are on the order of 300 bytes, not kilobytes, not megabytes, not gigabytes, 300 bytes. Now, while they don't do much, it is illustrative of how low of an overhead our containerization technology has, right? And so obviously, when the smallest container you have is 300 bytes, that gives you a lot of room to put your application logic in there, right? We're limited in terms of app size and the number of containers you can run, typically by the normal resources you have on a machine. So, memory and CPU availability. But we try to stay out of the way so that as much of that device capability and resources are available to applications, and they're not taken up by the containerization or the runtime. We require about 128K of memory and flash to provide the runtime, and that includes the runtime, the core operating system functionality, and the hardware abstraction layer. This is obviously on Zephyr. Numbers are a little bit different on Linux, but on a Zephyr-based target, it's about 128K of memory and flash. In terms of performance at runtime, that is obviously dependent on the hardware, right? What you deploy that to, the capabilities that you deploy that to on the device. But we can actually achieve near native performance with WebAssembly through AOT compilation or ahead of time compilation. So we can get a lot of the same benefits of that virtualization, but we can do so at a very, very performant level because of the ahead of time compilation. Also, our runtime is designed to be event driven, and therefore, if you're not running active code, you're doing event driven development. You're waiting for signals to come in or handling interrupts. We're not actively running and spinning, right? So battery life and power impacts are generally not impacted. Let's move to the next slide, talk a little bit about Linux. When you look at Linux, there's a whole host of Linux, right? So you have everything from small embedded Linux that can actually run on microcontrollers, all the way up to big data center supercomputers and so on. The goal of what we're trying to do is be on that smaller side of the Linux, right? Linux devices. There's a tremendous number of devices out there that are embedded Linux. They might have a CPU, but a very low end CPU. They might be limited in memory. And so we want to be very, very conscious of what we use on those targets so that we can leave as much available to run real applications on that. So if you take, for example, an embedded Linux device that has, say, 512 megabytes of memory. It's a fairly large amount of memory if you're coming from the embedded space. But if you're coming from the Docker side of the house, that's very, very small, right? And so if you're trying to run Docker on that and containerize your application, you're really limited by that memory. You don't have a lot left over in terms of doing that, because the overall containerization solution and everything that's needed to run that consumes a lot of that. On our side, we're a tiny fraction of that 512 megabytes, because again, we're designed initially to run on these embedded systems. So that leaves a lot more headroom to run your application, either larger applications or more of them. If I jump over to the next slide here, I'm not going to read through this. I think these slides will be available, but what I like to do is compare and contrast Okra containers to OCI containers. So one thing I probably didn't make super explicit before is we try to make the experience as close to OCI containers as possible. Obviously, some of those things don't make sense in the context of an embedded device. So for example, OCI containers typically have a layered union full file system that gets virtualized and things of that nature, or you might have a L2 virtual networking and NAT interfaces built into that. The overhead of that just doesn't make sense on an embedded device. But the idea of being able to access storage or being able to communicate between containers or make network calls does. And so we have analogs for those. So for example, on an OCI container, I mentioned we have that layered file system. We can do volume mounts. On the Okra side, we have resource files, so you can have blobs and you can address those as files. We have a simulated file system that has a POSIX-like behavior, but we don't offer direct file system access for obvious reasons. On networking, we don't have virtual networking NAT, but we do have a managed network socket API. We do have messaging service and service location so that containers can be communicate and coordinate between themselves. So a lot of detail on the slide. It's great to look it over, and obviously if you have any questions, you're more than happy to reach out to myself or the rest of the team. To wrap up, there was a question earlier about like how does this impact drones and what can we do here and so on. So in terms of the use cases here, there are many, right? So we're really targeting nodes, and our sweet spot is somewhere between 256 kilobytes and about 2 gigabytes of memory, right? Above that, we have tons of solutions. You have a lot more overhead. Docker starts making a lot more sense, and traditional containerization solutions really shine above that 2 and 4 gig limit of memory. But below that and between this, there's a lot of devices in here. There's drones, there's parts of your car and your appliances and smart connected products and smart machines and machine interfaces and things of that nature. And so this is an area where there's the sky's the limit, and there's a tremendous number of use cases that can happen there. If you have a product that needs to be updated frequently, you have a product that needs to be specialized or software defined, this is a great technology for that, right? So things like machine learning, where I want to update that model, right? I might have object detection and I want to update it so I can detect additional things, or I want to specialize that to do things like people counting, right? Or I have a drone and I want to do inspection of pipelines or inspection of overhead high voltage cables. You can encode that in there and you can run that inside of the drone. And the nice thing about something like a drone is you could have your flight side controller, which is all real time, traditional embedded systems, and alongside that run containers to do things like the inspection logic, right? And that same pattern can happen in an industry, smart cameras, and others. So now I'll hand it back over, so we stay on time. I'll hand back over to Jason, and then we'll talk, move over to the next presenter, talk a little bit more about an actual use case in the industrial space.
All right. Yeah. Thanks.
Over to you, Jason.
Thanks, Stephen. Yeah, I'm having some problems with video, but yeah, and there was a question from John around WASI support and how does that help with the interfaces to devices and kind of specific I/O below. And so this is a great segue into the next topic where we're going to talk about kind of OPC-UA and the requirements and the considerations of how you would interface with the outside world through WASI. One thing I would say, as well as a key delineation, is WebAssembly is an enabling technology, but the goal with Ochre is package that up into a full container runtime that also includes APIs and provisions for starting and stopping containers, managing security permissions and whatnot. So that's the big difference between WebAssembly and Ochre. It's packaging it up into a kind of a full solution for that device that then you can use with your console of choice. Cool. So with that, let's move on. I will hand it off to Nick and Dan. If you guys want to do a quick intro and then kind of dive in.
Sure. So I'll start. Hi everyone. I'm Nick Yameen. I'm a senior firmware engineer at Schneider Electric.
Hey everyone, I'm Dan Kouba. I am a senior solutions architect here at Atym. Great to be with you all. Next slide.
All right. So before we start diving into the details of our proof of concept we're working on, just briefly want to introduce Schneider and Atym. So Schneider, our purpose is to be your energy technology partner for all. That can be individuals all the way to businesses. So we heard from Merrill earlier today, and we're part of the industrial automation space. So how do we, as in IA, create impact for our customers? Well, first, we want to lead in digitalization and automation, as well as drive software-defined automation. We want to leverage the new technologies like containerization and orchestration to make the future more open and intelligent. We also want to increase energy efficiency for our products, as well as workforce efficiency for our customers, making their lives easier. And finally, we want to make industries as sustainable as possible. So Dan, can you introduce Atym briefly?
Yeah, sure. And you've heard from a couple other Atym folks today. But as many of you have heard throughout the talks here, that we're really trying to help folks like Schneider develop applications with cloud native technology, but with the edge as the end deployment. And now we're building on top of Ochre, our open source runtime, a system that allows you to orchestrate containers at the edge, be able to do the ahead of time compilation that Stephen had previously mentioned in his session to allow you to get native performance at the edge, and also give access to device fleets for remote debugging and access for device management. So we're building that sort of application and device management infrastructure on top of the Wasm runtime that we're all really excited about today. Next slide.
Cool. So I want to highlight some of the gaps and challenges, but before I do, I want to give a picture for everyone about an example segment within Schneider Electric. We can take a look at our consumer packaged goods, and you can see that in a factory like this, there are hundreds of devices from meters, sensors, actuators, controllers like programmable logic controllers, edge devices, and even industrial software. So you know that there's a lot of moving pieces, a lot of communication going on inside a factory. If you can go to the next slide, please. So with that picture in mind, there are some gaps and challenges that we see. First, around cybersecurity and interoperability. When you have a factory like that has so many devices, you want to make sure that the products you use have up-to-date standards on cybersecurity, as well as as you start including more and more, more and more products into your solution, we see that there's no interoperability between these devices. So the slides did disappear, but there is a picture there, and we see that there, in between different segments of, say, like a process or even machinery, you can have different protocols communicating between the two of them. And even trying to talk to systems outside of industry can be difficult at times. And oftentimes when you want to connect everything together, it entails an extra cost. So our customers would have to pay more to get everything working as one ecosystem, to say. So
I think we're getting the slides back here. Sorry, everyone.
Cool.
One more.
One more. Yep.
Perfect.
There we go. So I tried my best to talk to it. But yeah, like I said, you see these devices using various protocols like Ethernet, IP, HART. And so it's just very hard to get everything working together as one system, and that extra cost to actually get things talking together. So our vision, what does that look like? We want seamless information exchange among these devices and apps that are used in the factory. So things from small embedded devices up to higher edge devices. We want to have something easily customizable and allow our customers to adopt easily as well. Next, openness. We want our vendors to be able to use these open standards to actually include third-party products, applications into our systems. And then finally, a future open architecture. So as things progress in the world, we want to be able to take changes as they come. If you move to the next slide, please.
Oh. Perfect. So one of the things that Schneider came to us looking to help them with is actually being able to help do those deployments and get different containers out to these devices that contain a lot of the same code, but are on different architectures. This is one of the things that Ochre really helps us with, and this is sort of in this first column of accelerating time to market, being able to prototype on full-blown Linux computers, but also be able to deploy to embedded devices without significant recompilation or dependency on silicon. That layer of abstraction is something that we're really excited to help bring to the market with Ochre. But there are other benefits too. As was mentioned in the panel, some of the awesome things about Wasm is it's a permission granted for every piece of access that it has outside of its own sort of math-based CPU. So anytime you need to access memory, anytime you need to access the network, you actually have to grant those permissions to those individual modules. So by default, it's actually a fairly secure interface, and it allows devices that don't necessarily have a hard MMU inside of them to act in a memory safe way. So deploying something like we're going to talk about OPC UA in that framework can add additional developments or additional benefits other than just being able to deploy those containers to devices fairly easily. And finally, we also see a lot of applications around bringing Edge AI into the picture here, being able to develop in any language and being able to deploy models in a fractional way. These are all really cool things that we're excited to bring to the market with Ochre. Next slide, please.
So some of the goals for this use case and proof of concept we're collaborating on. First, we want to demonstrate that the capabilities of Wasm and WASI for embedded devices, that it actually works in the industrial automation space. We heard earlier that we want these devices to be basically running for years on end. So is this the technology that can help us enable that? The second piece is that the OPC UA concept would enable future use cases within industrial automation. It would be a stepping stone for more complex projects and problems we want to solve. And finally, we want to something that would be contributed to that future open architecture. Like I said, both Wasm and OPC UA are based on open standards, so it's great that we leverage the community for this.
I think one of the really cool things here is that we're building a foundation with WASI, Wasm, and the Ochre platform, but then we're taking another foundational technology with OPC UA, and we're building on top of that. And when you get to the application layer, now everyone can leverage, with many businesses and many different use cases, the foundations that are built here. Every incremental step we take towards progress on any of these technologies enables us to do more and stand on the shoulders of the work that folks have done before.
Exactly that. So I'll briefly touch upon what is OPC UA at a very high level. If you don't know, it stands for Open Platform Communications Unified Architecture. It's a mouthful. But what it is, it's a standardized communication framework that is actually standardized by the OPC Foundation. So at a very high level, first, it is used for data exchange, to have that machine-to-machine communication between very small IoT devices to things as on cloud IT infrastructures. So that helps us enable that interoperability between components. Next, it's also a flexible and powerful data model. OPC UA is a single language that can be understood across domains, whether it's in that process or discrete or even outside of industry. So that allows us to be able to communicate between our devices seamlessly. So we see in Schneider that OPC UA answers a lot of the use cases for us for machine to process, as well as enabling the interoperability across vendors. But it's very important to note that OPC UA is more than just a communication protocol. It's a standardized framework, an open unified architecture, right? That should be leveraged in industry moving forward. If you move to the next slide, please. So what are some of the benefits between Wasm and using OPC UA? Well, in Schneider, we see that the benefits of Wasm directly complement a lot of the OPC UA features. And earlier today, we heard a lot of great things about Wasm. So I just want to touch on a few points. The first one would be about the portability, that compile once, run anywhere, and how that directly relates to the modular design of OPC UA. When you have these very small Wasm modules, it's very easy to just take the single Wasm module and deploy it across a fleet of devices without reflashing the device, right? And so we see that work with OPC UA because of the future openness to adopt new changes as the standards evolved. And so once something like that happens, it's a simple recompile and then deploy to the device. The second benefit that I want to touch upon is the security piece. And I think Steven said this earlier, it's adding layers of defense and depth. So OPC UA has a whole slew of standardization around security, about how devices communicate between each other. And adding WebAssembly and WASI is just another layer that would help protect our WebAssembly modules and applications. Move to the next slide, please.
Cool. Yeah. So you've seen a piece of this slide, but one of the things that we've been working on with Schneider in this project is the ability to leverage some of the cross-platform capabilities that we have with the Ochre runtime. So what we've actually been able to demonstrate is the same binary container running on both a Raspberry Pi and also on a Zephyr-based board, this STM32U585 board. Although we have a host of boards that we support, so we'll also run on those. This is a great piece of technology to leverage this because it really just requires network access, and so any board with a network controller can realistically run this. So we're really excited to have been working towards this goal, and it's something we've excitedly been able to achieve as well. Next slide. So as Stephen went through, this is sort of what that runtime looks like. down under the hood here, with a lot of those common components being shared across both the Linux and Zephyr versions, and of course any other operating system too. While these are the two that we support today, it is definitely possible to bring this with fairly minimal effort to any other RTOS. But there's some major components here that I want to call out that we're going to talk a little bit about the effort that we actually went through to do the port of OPC UA to our runtime, and also some of the considerations that you want to take into account if you're going to be doing a similar effort. So the major pieces here, obviously you have the application itself, and that application might need some changes in order to support the capabilities of Wasm and WASI, as well as the runtime that we use called Whammer. So the application, we've got the virtual machine, which is called Whammer. And then we also have the WebAssembly system interface, which is WASI. And then finally, there's some platform architecture stuff at the bottom too that we've also written that gives access to certain particular hardware peripherals. Now, while OPC UA does not specifically use those peripherals today, we actually have instrumented some of those things for performance reasons, and we'll go into that at the end. Next slide. So some of the considerations that we took into account when we were scoping this project out and looking at it from a low level, how are we actually going to accomplish the goals here? When we looked at the existing application, we wanted to see, because WASI supports a variant of libc, what libc functions are we actually calling? And do we actually need to do all of the things that this architecture or our application requires? So this is a good place to start, looking at the depth that you actually need to port. And then additionally, are there any specific pieces of hardware that need to be accessed in order for this application to realistically run? And in this case, we are really focused on network access, and so OPC UA is a network protocol. And thankfully, socket support and all of that is pretty well supported inside of WASI and inside the runtime that we use with Whammer. One of the performance related thing here, because of the security boundary that's around these containers, we do want to take a pretty careful look at how many different calls are being made across the boundary that actually cross from inside of Wasm and back to the host, or from the host into Wasm, because there is a performance impact of that security layer. It does take time for some of the memory checks to run and some of the other pieces, memory locations to be validated, because Wasm modules have their own separate memory space. So we did want to take into consideration some of the how many calls are being done across that boundary to make sure performance was going to be adequate for this. So when we start to look at just libc, let's go over to the right side of this. This is really implemented in that WASI layer and also in the Whammer layer. So we had to make sure that for all the libc functions that were actually implemented in the application, that there was an implementation in WASI. And thankfully, with a lot of the socket work that we've done, almost all of the required stuff was in there. So we didn't actually have to do any specific work in WASI to get this working. Thankfully, this is an area of the platform that's really well supported right now. But that's not necessarily the case if you're working with something specific. Like I was just working on a project with Linux's socket can interface. Not all of those options are actually supported in WASI, and there's certain different socket calls or variants of the arguments there that might need a little bit of work. But thankfully, we didn't have to touch this layer in this project, but it is something that you need to consider if you're looking at porting an application over there. And then finally, what's sitting under that with the Whammer layer, this is really where all of those libc calls get implemented at a platform-specific level. So Whammer supports a lot of different platforms. We, of course, are taking advantage of the POSIX layer for Linux, and then the Zephyr layer for Zephyr-based applications. And you need to make sure that there's an analog for each of those libc functions to make sure that it actually is going to call something at the end. If it's not implemented, it's going to call a stub function. And we did run into a few of those in the Zephyr layer that we didn't need to implement, although it was actually fairly minimal. And I'm really happy to say that the support is fairly well put together there on the Zephyr side. Now, when we look at some other very specific hardware access things on the left side, looking at the Ochre platform abstraction that we offer, there are certain things that we're doing over there, like supporting things like displays or GPIO, that someday might roll up into these other open source projects as sort of a generalized systems interface for those different items. But for now, we have been building support into our Ochre layer for some of those specific hardware peripherals. GPIO is the most relevant one here, and I'll talk a little bit about what that looks like on the next slide. So when we were going into this, how do we actually go about doing this porting? Those are all the considerations that we took into effect, but what does this actually look like in practice? So to identify some of those dependencies, as I was mentioning with libc, we use 2 different tools to do that. There's a really cool tool called Wasm tools that allows you to take an existing Wasm module and actually dump out all of the imported functions, among many other things too, that help you can debug something. But we were able to look at all those imports and say, hey, okay, these are all the things I need to call. Do these actions that gave us that list that we can actually go and then validate against what the WASI and WAMR layers provide. But there's also a way to do this at runtime as well. We instrumented the WAMR runtime so that every time it was making one of those calls across the boundary, it would actually make a print and say, hey, I'm calling this function with these arguments. And as you're going through and something fails at some point, it's really, really helpful to see, oh, that happened right after I made this specific socket call. Maybe it's an argument that's not set up correctly in a cross-platform way, or maybe something isn't implemented. So these are both really, really helpful. And then we also had to implement some platform-specific implementations in that layer. And in order to do that, it was really, really helpful for us to actually use the live debugging that's available in WAMR with the Linux runtime. So when we were targeting a Zephyr device in this, we were actually able to do all of this debugging on the Linux runtime and say, hey, these are the things we can call, these are the arguments that I'm expecting, this is the return value I'm actually expecting, inspect the stack, inspect the call stack. It was very, very helpful to do that. And we didn't actually have to go necessarily do that on live hardware. And then, of course, we had to do a little bit of implementation. So, as you're thinking about these things, you got to ask yourself, where do I put these pieces that I'm developing? Is it going to go into Ochre? Is it going to go into WAMR? The way that we typically think about this is if you're doing things that are around application, container architecture, and management. So things like, oh, I want these 2 containers to talk to each other. Or, I want to make sure I can start up this container on this particular piece, this particular type of input. That's probably a great thing for Ochre to manage, because it is that container management architecture. When you're looking at hardware abstraction, that's probably something you want to think about contributing to WAMR, or looking in WAMR to see if it actually is supported there, because that at the end of the day is going to perform that cross-platform implementation of all the things you want your program to do. And then finally, this is some of the performance evaluation pieces that I was bringing up. We had a cool opportunity to help the Schneider team instrument their runtime in a really low-level way to make sure that we were able to catch calls that were happening inside a container at exactly the time that they were happening. And the way we're actually able to do that is we were able to share memory across the Wasm boundary. So a chunk of memory inside the Wasm container is exactly the same chunk of memory in the host container. And we're able to map the GPIO registers directly from the CPU that we had. We were able to do this in a cross-platform way. We did this on the Raspberry Pi. We also did this on the U585 board, so that you could write, do an atomic write to that memory location and drive a GPIO bit high. So exactly when something happened, we were able to see on an oscilloscope or in a logic analyzer that a particular event had occurred. Next slide. So at the end of the day, if we roll this all up, what did it actually look like to do this? We had to do a few things to match WASI's capabilities. But we actually made the choice to do these in the application. There weren't that many functions that we actually would have needed to implement inside of the WASI and WAMR layer. And so we just implemented a few shims. A lot of these have to do with networking functions that expect like a host file or something like that to know what local host is. And so we just implemented some stub functions that returned a particular value that we knew in order to do this. But we wrote a couple hundred lines of code to support these functions. And that gave us everything that we needed in order for this to actually be compiled successfully into a Wasm module. That ran on Linux, which is pretty amazing. It was really cool to see that once we got those functions implemented for it to just work. Now, it took a little bit of time to do this on the Zephyr side, because not everything lines up in Zephyr the same way it does in POSIX. And so there were a few functions we needed to implement, mostly around multicast and some other things, but it wasn't a huge amount of effort. And all of this stuff is going to be contributed back to the community. So hopefully these results can be also shared. I see you've got a question about if there's an OPC UA stack that has already been ported. there is not at the time. That's why we were exploring this. But I'm happy to say that it was not an enormous amount of effort for us to do this, and we're really excited to be able to share this back to the community as well. Next slide.
All right. Sorry, you want to say something, Dan?
No, go for it.
Okay.
Yeah, let's talk a little bit about performance.
Okay, so I'll talk just briefly about what we're doing here in terms of the performance testing. So like Dan said, there wasn't any OPC stack at the time that natively ran within WebAssembly. And so we ended up choosing, it's called Open 62541. It's available on GitHub. It's a OPC stack that supports the publisher and subscriber model. And so what we are trying to leverage here, so we have two separate tests. And in these tests, we have one Raspberry Pi as a publisher and one Raspberry Pi as a subscriber. And in the publisher, the Open 62541 stack is actually compiled into a WebAssembly module. So it's just that application running as a publisher in Wasm. And so for the first test that we're actually going into, it's we're calling it our deviation tests. So what is happening is that a publisher is repeatedly sending messages to or publishing messages to the subscriber. And so what we're measuring here, we want to see how much the time deviates between actually sending the message and receiving it on the subscriber side. So if you think, if we publish every 1 second, then we should capture the message roughly every 1 second as well on the other end natively. What does that look like for Wasm? So in our tests, we're comparing the two, the native open stack running versus the stack running as a WebAssembly module. And hopefully we'll see with the performance of WebAssembly that we have near native speeds. We don't know how much it differs yet, so that's what we're trying to strive for. The second piece that we're actually looking into is our GPIO test. So in this scenario, it's the same setup, but instead we have a network tap that's in line with the publisher and subscriber. In this scenario, the subscriber is just there to receive messages. It's not actually doing anything, but again, we have our publisher as a WebAssembly module that repeatedly sends messages out onto the wire, but it also triggers a GPIO pin. So what Dan was saying earlier about the GPIO being leveraged in the Ochre runtime, we're actually using that on our Raspberry Pi. And so with this wiretap, it will read the GPIO pin and take a measurement when it received the network packet. And so in this test, we're really looking for when the GPIO is triggered versus when it's received. So a lot of this test that we're doing is to see if Wasm really fits our use cases within industrial automation and that future open architecture.
And before, just real quick, before we get into the demo, one of the really cool things we're going to be able to show once we've completed our testing here is actually the performance difference between interpreted Wasm code and the AOT compiled code as well. That's something that is a particularly interesting part of this technology, and we're excited to be able to have some real world data to share in the future that will illustrate the benefit there.
Definitely. All right, so we can show the demo next. Sadly, at this time, we don't have any performance data. We're actually actively working on that, but we did get the publisher working within a WebAssembly module. So that's what we wanted to show today. So on the left-hand side, that would be the publisher. On your right, that is the subscriber terminal. And so here we're just showing that it's a WebAssembly module. If we look at the file of it, and then we can actually start the subscriber piece. So like I said, the subscriber is not actually a WebAssembly module. So what this application does, the subscriber will just print the time every 1 second. And you can see the time's wrong because the publisher is supposed to publish that messages. So the year is 1601. So we'll start the runtime, and then you see the WebAssembly module get loaded and actually starts. And so the publisher will publish every 100 milliseconds, give or take, and then the subscriber just prints it every 1 second, just so it doesn't flood the screen. And we see that it's receiving the updated dates, and if we stop it, it stops getting the updated dates as well.
Awesome. And we've actually been able to demonstrate, we don't have a video of it today, but we've been able to demonstrate this same module running on that U585 board. Nick, these are on Raspberry Pis, correct? Is that,
Correct. Yep.
Yeah. So we've been able to demonstrate exactly the same thing on the Zephyr-based runtime that we have, which is a really cool example of the cross-platform capabilities that we have.
Yep.
Awesome. I think that's it for us.
Yeah, no, very good. Yeah, we just to get back on track, we'll have open Q&A at the end as well if anyone has questions. But yeah, excellent. So it's, one of the key takeaways here is once this work is done and we're contributing it back to the community, that module can be used across the runtime on any different device rather than having to compile all that functionality into each device and specific to that hardware. So this can be multiplied over any type of capability, and then as well Edge AI, which we'll talk about here in a little bit. Yeah, great stuff. So with that, we'll move on to the last panel. We've got about 40. And this will be about kind of use cases and the why around Wasm containerization and kind of the benefits for businesses. So bring on the panelists here. Let's actually go in reverse order, and Ellen, have you start. If everyone can provide a quick introduction, on you and your roles, and then we'll dive in.
Yeah, sure. Hi everyone, my name is Atym Wu. I'm currently an R&D manager in Schneider, and working in the CTO office of the Industrial Automation business unit. So I think I want to just kind of share my kind of starting point of the journey with WebAssembly. I think it was almost 2 years ago, and then we started, from the friend chatting to say, hey, you may want to check this technology, it's a cool thing, or WebAssembly. And then we were like, okay, I started to look at the webinars online, and then, okay, it starts as a web-based application. I'm like, okay, cool, but my work, day-to-day work is always around firmware, around devices. So I'm like, maybe not related, but until, I keep watching, keep learning. And then until one day I saw this Wasm presentation, I think it's a couple of years ago, about the runtime and then about the WASI, the system interface. I think, we have mentioned that before today in the session. And then, wow, it was like a, fresh and air, and then nonstop. I keep watching and keep learning. And then I think our team keeps catching up the sessions, the webinars, the repositories, and then we kind of try to engage, in the community and, share our investigations. So after 2 years, yes, here we are, kind of also want to engage and share with you guys our discoveries, our investigations. I have to say that, even although our experience with Wasm, was not like from the beginning, it was like limited, a couple of years, but still there's quite a lot to catch, quite a lot.
Yeah.
So, yeah.
Yeah, cool. Felix, you want to do a quick intro? Yeah, Ellen, we'll come back and kind of talk about some of the specific use cases you guys have been building. Yeah. Felix, quick intro.
Okay, yeah, absolutely. So my name is Felix Nilsson, and I work for HMS Industrial Networks. I've been working there for 6 years. I'm working in the industrial networking division, which primarily develops and sells the NBS line of products. I mainly work with our edge computing initiatives and emerging technologies.
Very cool. Marshall?
Hi, my name is Marshall Meier. I'm a Director of Engineering for Instrument Connectivity here at Emerson. We're a global industrial technology company. And my role is really about developing connectivity technologies that we can roll out across Emerson's various Dell devices.
Cool. Last but not least, Dan.
Hi, everybody. I'm Dan Dumitriu. I'm CTO of Midokura, which is a Sony group company. In particular, we're a subsidiary of Sony Semiconductor Solutions. And we work on embedded devices and edge AI and sensors. And so I would love to tell you how we ended up using Wasm in our product line, really out of necessity. Thank you.
Cool. So one of the questions that we have is why now? This has been done a long time. Ellen, you mentioned a little bit. Maybe we'll start with you. I mean, you mentioned a little bit about kind of you've done firmware for a long time, and then the talk about WebAssembly piqued your interest. But we'll get into specific use cases, because this is ultimately about not a solution looking for a problem. This is about business need, and so we want to dive into that. But thoughts, Ellen, kind of then go around like why does this matter now compared to how we've always kind of done things?
Actually, I think from I'd say my experience with firmware engineering. I mean, I started in Schneider as a firmware engineer. Before that, I was not in the embedded. It was not like very long, still single-digit number of years. But I feel like even with this short amount of time, I feel like we have kind of is tremendously amount of experience of. I think everyone is struggling with monolithic firmware, development. Sometimes during that time, I feel like your sense of time is changing. That sometimes you feel like slow. That because you have to wait for the duplicate, the building the image, and the debugging, testing, and especially when there are cross-team collaborations, a lot of time, and when there are also dependencies between teams, there are a lot of time you couldn't control, and you feel like it's not efficient. It's you're not efficient for engineering. So I think we've been through a lot, and we keep looking for a different way of firmware engineering. We're looking for a game changer. So then we started to look at the containerization, modularization, virtualization. From the standpoint, I feel like after understanding what it is, how it works, I think from both engineering aspects and the customer's aspects, we think this is a good, a match of what we need. From the engineering side, we want to be efficient. On top of the agile process, kind of help you to manage your project, your process. But the delivery from different teams, we need the structure to be pluggable, to be modularized. So in that case, the between teams, we can collaborate in a way that is efficient, and also each team can manage the backlogs in a way that could be integrated easier. And then if you look at on the customer user side, these years, the customers keep looking for independent scalabilities, right? They want easy deployment, fast upgrade, and even with some customizations. So I think all those needs, we can realize them within the world of containerization. And now we see that WebAssembly, this technology, has the potential, even now it's still under development, but we see that it has a potential to help us reach this vision that from the engineering side and from the customer side, we couldn't wait. That we are looking for this game changer for a while, and now is the time for us to put it together and deliver it in a way that is faster, easier, and kind of both of us will be happy, from two ends.
Yeah. So let's riff off of that. Kind of the related question. The first one, Marshall, maybe if you, from an Emerson standpoint, how what kind of specifically drove you into looking for containerization solutions? I mean, I think it's kind of similar in ways to Ellen, but just kind of specific to your context would be great.
Sure. Yeah, Emerson is a large, as I mentioned, industrial technology company. We make and sell equipment and software that are used to run critical infrastructure, chemical plants, pharmaceutical, life sciences, manufacturing, energy. And we make all sorts of different devices. So things that measure pressure, temperature, level, flow, analyzers, as well as control valves. So really the things that help run the plant. Like a lot of people in our companies in our business, we were built up through acquisitions, and we don't have a single engineering team. We have literally dozens of engineering teams around the globe. Now, one of the things we've been focusing on a lot lately is trying to drive more platforming within Emerson, and that can be a challenge because we're trying to operate, have a consistent experience and technology across all these different devices that were developed by different product groups around the world. And the way we've been approaching that, and what makes, I think, containerization interesting for us is that we do have globally distributed teams that are trying to work together on these new platforms. And we may pull in developers from around the world to develop the common parts of the platform, but also having the different field device groups be able to develop their unique part of the design that will run on the platform. So having containerization makes that a lot easier, I think. We may have containers for common functionality around communication protocols and security, but then separate containers for measurement specific or flow control specific functionality, such as measuring pressure or controlling the valve. So by having something like containerization, it allows our global teams to work more effectively together rather than everybody trying to operate in the same code base, and really just not enough elbow room for everyone to work together.
That makes sense. Dan, obviously you've been working with WebAssembly at Midokura for quite some time. When we were starting up with stuff at Atym, we saw a blog from you. I think it was maybe 3 years ago now or something, and
maybe 4. Yeah.
Like when I mentioned earlier with Chris at Siemens, like we got to talk with that guy. Steven reached out, but maybe kind of what are some of the reasons you guys started looking at it at Midokura?
Yeah. So we started from really a very kind of narrow technical need, right? So of course, like Marshall mentioned, there are all these benefits, but we actually started with one small problem, which was, so we're building this sensing device, which is essentially a programmable smart sensor using computer vision at the edge, but it's not necessarily only about computer vision, but essentially it's running some sort of inference at the edge, some sort of model, neural network, et cetera, what have you. So we realized fairly early on that actually the sensor doesn't just run the model. It has to do at least some other post-processing or processing of this data before it sends it off to the cloud or wherever that happens to be. And so there's got to be some code that runs that processing. We need to update this code over the air because these are not fixed function devices. And also, these are not necessarily running Linux. So there are a variety of different types of form factors with different computational power, the smallest ones being microcontrollers. And they're not running Linux, they're running Zephyr or what have you. Actually, we were initially running NutX. And so we need to do over-the-air updates, and we need to do them safely. So, lo and behold, we need a sandbox of some sort. So we looked at a variety of different technologies. So, we could do this one of many different ways. This is not the only technology out there that would let us to do that, but it is the only one that would run at near native speed. That was actually an important point for us, right? So we're doing like a high frame rate, maybe 60, 120 frames per second, processing of the sensor data. We need to run this stuff pretty fast on a very small embedded platform. And so we started looking around, benchmarked it, and WebAssembly, in particular WAMR, with ahead of time compilation, was the perfect fit. Mind you, at the time, I would still call this bleeding edge technology. So it would took us a while to convince conservative firmware engineers and product managers and engineering managers to take the leap, right? but we did manage to do that over the course of a year or so. And, it worked out well. Now, once we had the basic function of isolation in place, then we got more ambitious. And we said, well, okay, now we could start defining a more complex structure of what is an edge application. It's not just like this one piece of code. It's maybe several modules that are strung together to do some sort of pipeline processing. Maybe they can also interact with local devices, not just sending stuff to the cloud. To your point, like OPC UA, maybe there's something connected with OPC UA locally. We have that OPC UA server also running inside the WebAssembly environment on the edge device. So the flexibility also came out of it. But I would say initially, we really needed to solve this one particular technical problem, isolation and safety. And then once we have that in place, then we got all these other benefits, along the way.
Yeah. Great. Yeah. So, the Edge AI, computer vision, one of the killer apps for Edge. It's just AI in general. And as we talked about before, like models inherently change, over time. So a set it and forget it approach doesn't necessarily apply as we go forward. Felix, you guys from HMS kind of looking at it from a different business benefit. Maybe talk a little bit. I'm sure similar benefits too, but also there's a business benefit of why it could be interesting to you guys.
Yeah. So really, we have been looking at what you could call edge computing, or being able to run custom code on our devices for quite a long time, and we also have a history of enabling it. So our devices historically, and still to a very large degree, are, if you look at the spectrum that you showed before, it's definitely further to the side of the constrained edge device.
Closer to tiny.
They're along the size of the tiny. Maybe not the tiniest of tiny, but very tiny. So Linux is, for most of our devices, definitely out of the question. But historically, and still, of course, we have devices where you can extend the functionality using the likes of Lua and Java and Basic and various other scripting and non-scripting languages. But those don't really offer all the benefits that you get with containerization. And then you have trends now where we see that partially we have this consolidation going on inside the hardware, where historically you have had a design where you have multiple CPUs or multiple microcontrollers doing one single task, and each company or person adding in more functionality to that CPU. That is all going away for good reason. And now when the CPUs are more capable, suddenly we end up where you want to cram in as much functionality, usually from different vendors, into the same piece of hardware, and then you have new challenges. And also, as Nick brought up earlier on, the complexity of the communication is increasing quite a lot. So we're going from a period where we have quite a lot of relatively simple protocols, and now we're moving towards a smaller number of protocols, but with an increasing complexity. And we have sort of reached a conclusion that for the future, to deal with this complexity, this workflow that we have had before, where we develop products that are essentially configure, set, and forget, are not really feasible anymore. So, and what we think is the solution is to have devices that enable or allow for custom code execution, because the ecosystem has gotten so complex that making a device that suits every use case, and I think OPC UA is a great example of that, because OPC UA literally, as Nick said, it's a framework, it's not only a protocol, but that also means that making a single product that fits as many use cases as possible is quite difficult. And here, something like WebAssembly, I think, can be a great asset.
Yeah, cool. And I want to come back to, we've talked a little bit about kind of the amplification, element of things, but come back to that. So Ellen, kind of specifically, we heard from Nick and Dan, around LPCUA enablement and sort of that general connectivity element. Felix just mentioned that, but maybe also kind of talk about like, and you mentioned like the engineering, I call it engineering friction, or just like the complexities around working with across different organizations, business units. Marshall, you mentioned that as well. But there's also kind of just the general skill sets part, and the person that knows AI is not necessarily someone that knows embedded C code. Can you talk to that a bit, and kind of how you see containerization helping partition out even when it comes to just general skill sets?
Sorry, who was the question?
I was going to ask Ellen, but yeah, them.
Oh, sorry.
Okay. Okay. Yeah. So kind of back to. I mean, I wanna emphasize that AI now is like in the future. Definitely AI will be around us. We cannot avoid it. Cannot just hide it. It's like the smartphone. Decades ago, it's a new thing. It's cool. But still some doubts. But now you see, everyone is using, and it's commonized, and we all we feel panic without the smartphone, right? AI is similar. That we see that in the future, in our daily life, no matter it's life or work, AI will be there. AI will be there. However, nowadays you see that the large amount of the AI modules, machine learning, capabilities relies on large computation and power consumptions in the environment, in the infrastructure. But it's different from the cloud native, modules that embedded, that we have our realities. We have limited resource, limited memory and CPU, right? So in that case, we will have to think about how do we bring the AI modules into our embedded environment, which will engage some of the memory, CPU, resource management skill sets. I think that's part of the key and for this journey. And of course, WebAssembly in the middle. We see that it has the potential. It has the potential to allow us to bring the AIs into the embedded ways, align with runtime and kind of interoperabilities, between a heterogeneous device environment. And at the same time, we see that in the future, for example, when you have, I think previously there is a question about the robots, in the embedded environment. We need fast interactions and fast data processing on the embedded area. In that case, an AI or data processings, we need them to be processed on edge instead of going back and forth through the air, through the cloud. And with because of the reflection, because of the recognition, it also requires fast update of the applications of your module, of your recognition, your analysis. In that case, when we updated the applications, will involve in also the CI/CD, the DevOps, that process, the autonomous workflow to enable us to use the kind of fast update the recently learned data, recently learned models into the reality to take prompt response. So I see that so these are the skills I think is coming up and more needed. But I see that between, and it always happens that when there's new technologies coming up, we discover gaps in the skill sets, gaps in the areas that to tackle. But I think there might be more coming up, but I think that's the key for the community to working together and to keep monitoring to see what's the more opportunities, different areas that challenges in different businesses, different areas that we can put it together to drive this train to go to the future that's we're picturing together.
Just have one comment. So on the topic, it was mentioned that skill sets differ among different types of developers. We totally felt that because we're doing computer vision. So we have computer vision / AI engineers. And then we have these embedded engineers, and clearly they're doing totally different things. So, the AI engineers are programming in Python mostly, and the embedded engineers are programming in C mostly. And these are like two different worlds. Now, meanwhile, we do need to have these AI applications running on the edge. So typically what's happening is the AI engineer is, okay, we build the model, we optimize it, we compile it, down for the embedded device, for the DSP. And then there's like this post-processing code that was written in Python. Somebody else is now translating it into C, to run on the edge device. Okay, copying and translating code is always a great opportunity to screw something up, right? So that's not great. So we wanted to say, can we run the same code that we do during training on the inference side? That was the goal. And so, like I said earlier, we got a little bit more ambitious once we had the sandbox, and we sort of realized that Wasm could also allow us to do kind of multi-language environments, not perfectly, due to various constraints, but not bad. And so we built a very constrained Python kind of SDK just for this kind of post-processing of data. And then we integrated that whole thing into the training side, like in the pipeline of training, so that it would run exactly the same post-processing code as during inference. And we, of course, we compiled the Python down into Wasm somehow. Okay, there are a variety of different ways to do that. All of them are not ideal, but they do work. And so again, the point here was that we enabled our AI engineers to actually write code that could run on the edge device. I think that's actually pretty cool.
Yeah, totally. We've worked with folks where it's like, you get the runtime going, like in specific to Ochre, you get the runtime up and going, and then you get on with the machine learning person or the AI person. They're like, all right, what do I have to change to work, in this environment? And it's literally like the target directory. It feels just like Docker. That's they know Linux and Docker and whatnot. So it's really about kind of the embedded world, and I'd call cloud down and AI and IoT and web, mobile. They're all sort of converging. They've been converging for some time. Actually, I'm kind of riffing off of this topic. I'll bring up for future use case, and this is actually not really super future, is regulations like Cyber Resilience Act. I'll throw that out there as kind of a macro trend, that is kind of the impetus for relooking how we do things. Marshall, any thoughts on kind of CRA and how that plays into the interest here?
Yeah, cybersecurity, as you think about the process automation and discrete automation industry, is becoming increasingly important over the last several years. Historically, our devices were much simpler. They were running on legacy protocols, and cybersecurity wasn't as much of a focus. But as
security by obscurity was like the goal for me.
Yeah.
Like,
just protect the wires in the plant,
yeah.
And you should be fine. But our devices are typically very low power. But what we've seen as there's been advancements in microcontrollers, we're able to do more and more with them, and that includes adding more connectivity technology. So we talked about Bluetooth, cellular is interesting, Ethernet APL, which is a 2-wire Ethernet technology that can be used in very hazardous areas with in an explosive environment. And we're excited about those type of technologies because it provides the ability to get more data out of our devices, right? And try to help customers solve their problems with more data-rich devices. But the downside of that is now cybersecurity is becoming really top of mind. When you introduce wireless technologies, IP routable technologies like Ethernet, cybersecurity is something we really have to spend a lot of time thinking about. And one of the things we know is that you can do as the best job possible developing a secure product. There's certainly a reasonable chance that a vulnerability will be found, and you'll have to do an update with it. And this is something our customers are expecting from us. And now even we see with regulations like the Cybersecurity Resiliency Act, The EU Radio Equipment Directive is another example. I expect there to be other countries rolling out similar regulations. So having the ability to easily update firmware, and especially if we can just update the part that's needed, right? And that might be just the security part of the firmware and not maybe the measurement or valve controlling part of the firmware in our case. So being able to really containerize security specific functionality, or the functionality that is most likely need to be updated from the more long running functionality that doesn't, is certainly very interesting to us.
Yeah, and you mentioned Ethernet APL. I mean, these technologies. I mean, that's closed loop control and digital signals in the same wires. So that opens up a whole new realm of possibilities, and exposing to risk to networks.
Absolutely.
Yeah. So kind of turning from actually, one thought on cybersecurity. Like, one of the things that we see often, there's CRA, and how can we more programmatically address the requirements to some degree. First off, is understanding the requirements, because they tend to be, they're a little ambiguous still today, I think, to a lot of folks. But that's going into effect in 2027, so it's coming up. We hear also all the time, SBOM is a big topic. Where is the what's the provenance of the code that I use? That is more difficult to do when you're doing source code soup versus you compartmentalize and have binaries. We're also seeing a lot more discussion around memory safe code. C, which is most of embedded, is not a memory safe programming language compared to like Rust and Go and whatnot. But you can't just like change everything from C to over. You need a transition path. But if you can encapsulate that code inside of a container and provide some level of protection while you move to kind of new programming languages over time, as it makes sense, there's some benefits. But shifting gears from kind of the save money or reduce engineering friction to the make money, Felix, I know you've kind of had some ideas around just the amplification of things. Maybe talk about that a little bit.
Absolutely. So I mean, in the Linux world and in the cloud world, this is something that's been around for decades now, and it's obviously very, very, very successful. Being able to just concern yourself, like there are a lot of companies out there who have great ideas, who are very good at specific things, and they can realize that by writing an app or software or something, but they don't want to or necessarily know how to maintain an OS and make custom hardware and stuff like that. So what this really allows us to do is to run untrusted code on very constrained devices. And that, I think, opens up a whole new range of opportunities. We have been talking about AI, for example. And as we discussed, one challenging aspect there is that the people who develop the AI are usually not the embedded developers. They have a completely different skill set. They know different programming languages. They have different concerns. And for example, making sure that the underlying embedded platform is always running is something that's very important when you're an embedded engineer, because if something breaks, it's a pain to get it back alive. And if you're allowing other people, let's say an AI engineer, to deploy their software on your device, then you need to make sure that whatever is deployed on there doesn't crash your thing. And this containerization, I think, will open the door to that, where we can separate the concerns, we can separate the development cycles. And I would say that the opportunities are endless, because, I mean, a lot of people talk about AI, but at the end of the day, AI is just another piece of software. And I'm sure that there is an almost infinite amount of people and companies out there who will be able to generate a lot of value in these to them new markets when we open up the possibility to run containerized software on these more constrained devices. because there's a lot of constrained devices out there.
Yeah. I mean, it's by far by volume the biggest edge footprint. We're talking, tens of regional data centers, hundreds, or just hundreds, thousands, maybe to billions in the physical world. And you mentioned something like too is this notion of bringing together different apps, and including there's the control aspects, and we've been talking about software-defined controllers and separation of concerns. When that happens, while also managing the resources on a constrained device, so it's attractive from that standpoint. We're moving kind of from a physical separation of concerns of like a controller, and that's what it does, and then a gateway that connects to it, maybe pulls data out through OPC-UA, and then that connects to the broader networks, to a virtual separation of concerns, where you're starting to see the same kind of data functions on that device, and that's where containerization can really help.
And at the end of the day, it's a money saver because like we can add more value in using less hardware. And enable
kind of marketplace things over time, where people can kind of bring their own apps and run them on top of your environment, but it's not mixing together. Yeah, Dan, you have some thoughts on advanced class?
Yeah, just to the point of development cycles. So what we found is, I actually don't have a deep background in embedded development, but what we found at Sony was basically, okay, we made some change to the product. We need to QA the entire thing, all of the software in the same way, the whole thing. That's ridiculous, right? Like, okay, like you were saying, this has got to be a layered architecture. You got some stuff that more or less never changes, like the OS, et cetera. And you have the application layer that could change. If the application layer is isolated, you don't need to run the same level of testing, when you've made one small change to the application. So that's a big deal in terms of process.
Just this kind of stuff, complex solutions, a lot of different considerations, inherently wants decoupled life cycles of all of that development. Stephen mentioned trying to bring everything together to be compiled, on schedule, can be super challenging, especially when you can't even do it a lot of times without that hardware in hand, and you might not get the device hardware until later in the cycle. In this sense, you could run the exact same container on your Linux machine, prototype the whole thing, and then deploy that onto the actual target device on the fly.
That's true. We didn't talk about the emulation bit, but yes, that's something we also started working on. It's not there yet. It's actually a little more complex than that, just running the container, but yes.
You have to emulate the actual capabilities of the device.
Exactly.
You're not, trying to pack 10 pounds into a 1 pound box, but so to speak. But great, Ellen. I know you had a network issue, so great that you're back.
Yes.
Wanted to. It proves to everyone, just like some of the side things. This is real time. This is not pre-recorded.
This is so real. This is happening.
It's happening right now.
I'm trying to figure out different ways. Now I'm connecting to my phone, personal, the hotspot. I'm like, oh, right. That's the only way to bring it back.
You're coming through clear. So I'll bring it back to you. Like we're about ready to wrap up, but what are you kind of seeing, Schneider, yourself, for sort of future potential?
Thanks for that question. And I will check the video back to see, the panel, what other people talk. But I may duplicate some of the thoughts. But on my side, I think Schneider is driving this, software-defined automation, right? And now everything is software-defined. So I think Wasm is the right thing we should keep doing to have this capability to decouple software, firmware, and hardware. And eventually, we see that in the future, if the one or more hardwares will become affordable, that regular people can just get some affordable hardware and then can do some customized applications on the hardware, and then instead of running a small scope of automation at the manufacturing, at a specialized professional environment, maybe you can run something automation at home. To help you just do your cooking. You don't need to do cooking.
Yeah, it's becoming more
Thinking
accessible.
about
These types of technologies, and we're seeing a lot of stuff happening with the maker world and all that.
Yeah. But that's I think that's also how we. That's why we keep trying to see where we can go. I also feel like this is also like a Olympic game, right? So we keep pushing to see where the limit is. There may or may not be a limit. We don't know, but we just keep trying. And until we hit that limit, and we discovered a lot of areas that we can have a lot of fun. But I think this game we just started, and I think we should keep doing, and it's to see you don't know, and keep pushing to see what we can do. I always have this dream that, because I'm far away from my family, from my parents, I would want to see that one day if they can, I can get some reasonable hardware and then just put it at home, and then all the automation systems to take care of them. And then I don't know the concept of the automation of the robots are available, but still, if we can do some customization with affordable hardwares to kind of help their lives, because humans' life has due to the technologies and medications, our lifespan is getting longer. But when the people are naturally lose some of the capabilities, we use technologies to help them pick up the technologies, to helping them to still enjoy the life.
Yeah, I mean, the best technologies are disappeared in the background, and it just makes things better and kind of helps us out and all that. So definitely agree. We're at time. Wanted to thank you guys for participating, and look forward to continuing to collaborate. And as we've said throughout the sessions, the importance here is to work together on the undifferentiated heavy lifting and kind of the standards elements, and simplify things and stay ahead of standards when they're not available, and kind of buffer that. That's the reason for the LTS support. But so we look forward to continuing to work together. And with that, we'll have you guys drop off. We will close things out. We don't have time for Q&A, but definitely feel free to reach out to any of us if you've got questions or want to get involved. Just briefly to recap, this is all about helping to kind of streamline and modernize embedded development with Wasm-based containerization, bring some of those cloud principles to embedded. As we've talked about, a lot of it's time to market, lower engineering costs, engineering friction, as I call it, cybersecurity concerns. The notion of on-device AI is changing things, and there always is a question: is this ready for prime time? And that's why we're all collaborating together. And the embedded SIG and the related long-term support effort. Why we're working in Linux Foundation or on Okra, so there's vendor neutral governance, and it's kind of open to all to contribute to and use. So with that call to action, feel free to dive in. You can go to GitHub, get the Okra code, start playing with it if you want to get hands on. Reach out to Chris Woods or Stephen Berard on our team. If you want to get involved in the eSig, you can tap them online, on LinkedIn. And then also, if you guys want to get involved in LF Edge in general, you can always join LF Edge and contribute at more of the board level. But yeah, lots of opportunities to get involved. We're also working, with a bunch of other, kind of standards bodies. But this is about going to kind of figure out the base so we can, go drive business on the top side. With that, thanks everyone for listening, and these recordings will be available. And that's a wrap. All right. Thanks all.
Thank you so much.
Thank you.